Okay, we're continuing with section 4.3, projectile motion. Uh, this is a we'll do some experiments using projectile motion. I might even maybe do a little demonstration in the lab, but we'll save that when we actually do the ballistic pendulum experiment. The ballistic pendulum is where uh, we'll be playing with projectile motion. Okay. Let's see. Yeah, that was the last slide of the last lecture. Now we're here with projectile motion, and we want to look at the projectile motion. If you look at the little video uh, about projectile motion, you'll see that they separate the horizontal and the vertical components of a projectile, and that's what we're going to do here. You can see the little the red, the bright red arrows are the vectors, the total vector, velocity vector for this projectile. The lighter kind of orange, you can describe it as pink. The other vectors are the vertical one are the vertical velocity. It starts out large. The next one at B is about a half the size, and then there is none at C. Why not? Because there is no vertical velocity at C. It's come to zero, and then it reverses direction, and at Vy is downward at D, and then at E, Vy final is as long as Vy initial, but only in the opposite direction. Now look at the X, Vx. In fact, it's called Vxi throughout. Vxi is at A, B, at C. They don't show the component; they just show the red arrow because it is the same. Because that all you have is the X component of velocity, and at D it's the same size, and at E it's the same size. Now, of course, we're disregarding wind resistance for these experiments. You can't always do that, but in this case we're ignoring wind resistance. So Vxi is the same. The horizontal velocity is the same throughout the trajectory of the projectile, whereas the vertical velocity changes. So let's read the little boxes. The y component of the velocity is 0 at the peak of the path. The projectile is launched with initial velocity vi, and the x component of the velocity remains constant because there is no acceleration in the x direction. The only acceleration is the gravitational acceleration, and that is projectile motion, any motion of an object under the presence of gravitational acceleration only. Okay, so here we have we we just finished combining the x components and the y components. Now we're going to separate them. Vxi, you have an initial velocity, and the initial velocity in the x direction is v initial times cosine theta initial. Vy initial is equal to v initial sine theta. So those are just the components of the initial velocity, and we're going to use that. We're going to calculate everything based on that initial velocity and the angle that it's projected at. The angle is very important in this case. Okay, it's just those are the same three squares that we read earlier. X final equals x initial plus Vxi times t. And then Vy final equals Vy initial minus gt because its gravitational acceleration is in the downward direction. So Vy average is equal to Vy initial plus Vy final divided by 2. And so Vy final, the y final is equal to y initial plus 1/2 of the, basically that's Vy average times t. And then y final equals y initial plus Vyt minus 1/2 gt squared. We also have the Vy final squared equals Vy initial squared minus 2g delta y final minus y initial. So they're just describing the equations of motion for the y position. Okay. As a projectile is thrown at an upward angle, it moves in its parabolic paths, such as in the figure. At what point along its path are the velocity and acceleration vectors for the projectile perpendicular to each other? A, nowhere, B, at the highest point, or C, at the launch point. At what point along its path are the velocity and acceleration vectors for the projectile perpendicular to each other? Let me switch to the iPad, and hello, it should, there it is. Okay, so we break this into an initial velocity. We have initial velocity at some angle, and that, let me make it bigger. We have a initial vertical velocity and initial horizontal velocity. I should make that a straight line. Okay, now, at a moment later, the velocity will be less because why? It's being affected by the gravitational acceleration, even smaller here. And what is it at the peak? Well, it's zero. There is no vertical velocity. Why? Because of the gravitational acceleration is slowing it down. Now, at these same points, I'm going to cheat, and I'm going to copy. I'm going to paste it. It's the same there. It's the same there. It's the same there, and it's the same throughout its path. The horizontal velocity doesn't change. So at this point, we have a horizontal velocity at the peak. We have no vertical velocity, so all we have is the horizontal velocity. And let's change colors. Let's make it blue. But we have a gravitational acceleration here. So at that point, we see that it's not a very good right angle indicator. We'll see at that point, at the peak, the velocity vector and the acceleration vector are perpendicular. So that's, if we go back to the question, we can see at what point along the path of the velocity and acceleration vectors for the projectile perpendicular to each other. The answer is at the highest point, as I just showed you on the iPad. You have all horizontal velocity, so and the gravitational acceleration is downward, so that they're 90 degrees to each other. Now, at what point are the velocity and acceleration vectors for the projectile parallel to each other? Well, there's only, if you're talking about the total velocity, there's no place that they're parallel. Now, if you were to ask at what point are the velocity and acceleration vectors for the projectile parallel to each other, if you were to ask at what point are the vertical velocity and acceleration vector for the projectile parallel to each other, at all points, because the acceleration is downward and the vertical velocity is upward on the upward trip and downward on the downward trip, they are parallel to each other. But if you're talking about total velocity, which is the addition of the vertical and horizontal velocity, they're never parallel, because you never have a zero horizontal velocity. So the answer is nowhere. At no point are the two parallel to each other. Okay, let's continue on. The horizontal range and maximum height of a projectile. This is simple trigonometry that we're gonna study here. Okay. So the question is, what is the h? What is the highest point that the projectile will reach at position A? And that's the maximum height. The range is, you see the R at the bottom of the graph. How far will the projectile travel? Well, let's study this. Okay, we know that Vy final equals Vy initial minus GT. And we want to know that at what point the Vy final is zero. That when it goes up on its peak, the Vy starts off initially, it decreases because of gravitational acceleration, and at the peak, it's zero. At what point is the Vy final equal to zero? Well, we have we make Vy final zero. We have Vi initial, Vy initial. Oh no, it's V initial. That's the overall velocity. V initial times sine theta initial minus GT GT at position A. Well, let's solve for T. So TA is equal to V initial times sine initial theta divided by G. So that is the time it takes for the projectile to go up. For the projectile to go down, it's another TA. So so that's only at TA. That's only half its travel. Okay, now let's take this equation. Y final, the Y final being the H. It's the Y initial plus Vy initial times T minus 1/2 GT squared. Now we're going to substitute the TA that we got, Vi sine theta divided by G. We're going to substitute that into each place we see T in this other equation. Now you see that Yi is assumed to be zero here, so there is no component there. So H is equal to Vi sine theta times Vi sine theta over G. Now, where did that come from? Well, that's the TA. If you look at the, I hope you can see the cursor here. The VYT, that's this here. But instead of the T, we have the TA, which is Vi sine theta over G. Minus the 1/2 GT squared, well, we're doing the same thing. For the T, we're putting in the TA, the Vi sine theta over G squared. So if you work that out, you're going to see that it's Vi squared sine theta over 2 divided by 2, because we have from here we have Vi sine theta squared divided by G, and here we have Vi sine theta squared. Well, we're actually using if you combine these, you'll end up with a Vi squared sine squared theta over 2G. Now that's the height. That's the maximum height. Now for the horizontal range, we're going to do the same thing. We're going to use that same. Well, in this case, yeah, we're still going to use the TA. You can see it here on the end. Oops, I shouldn't have. This TA, we're going to use that same TA that we got back here, Vi sine theta over g, are we? Let's see. VI, yeah, VI sine theta over g. You can see that this TA here is this VI sine theta over g. So we have uh, x final equals x initial times VXIT, and we want to look for the longest range. That's VXI. Xi is assumed to be 0, so all we have is Vxi times TB. Well, Vxi is Vi cosine theta times twice Ta. In other words, because you need the travel time up and you need the travel time down. TB is the travel time up and travel time down, so you need twice Ta. So you end up with Vi cosine theta times 2 Vi sine theta over G, and you get 2V squared, Vi squared sine theta cosine theta divided by G. And there's an identity that 2 sine theta cosine theta is equal to 2 sine theta. We use that identity and we get that from this equation up here, we see that R is equal to V squared sine 2 theta over G. Now, R max is when sine 2 theta equals 1. Well, when the sine of 2 theta, when does sine equal 1? Sine is equal to 1 at 90 degrees. So when 2 theta is equal to 90, theta is equal to 45. So the max height at the max height is when theta equals 45 degrees, and it'll be Vi squared divided by G. That is the maximum range. And we'll see that if we vary, we'll have a slide that shows that 45 degrees is indeed the max, and every complementary angle, such as 30 degrees and 60 degrees, will land in the same spot. 15 degrees and 75 degrees will land in the same spot. And as a matter of fact, here it is. Complementary values of the initial angle theta I result in the same value of R. Why is that? Well, what you're doing, if you have a steep angle, you're spending a lot of time in the air, but your horizontal velocity is very slow. Let's take the other. So that's at 75. Your vertical velocity is very fast. Your horizontal velocity is very slow. So you go very high, but you don't spend that much time in the air. Let's take the 15 degrees. You've got a small vertical velocity and a large horizontal velocity. So you're going very fast, but you're spending very little time in the air. And it ends up that they're complementary angles. You end up in the same spot. So you can see at 60 and 30 at the same spot, and 45 degrees is the furthest that you can travel. So extra points, you want extra points, use the initial velocity of 50 meters per second and give me the range for 15 and 75. Calculate the range for 15 and 75. Calculate the range for 60 and 30, and calculate the range for 45. Also, tell me how much time it's in the air for 75, 60, 45, 30, and 15. And you'll convince yourself of that. And if you do that, I'll give you extra points. I'll see where to add it, but I'll give you extra points. All right. Rank the launch angles for the 5 paths in the figure with respect to time of flight from the shortest time of flight to the longest. Well, I just gave you that information. At low angles, you've got you're very fast in the horizontal direction, but you're not spending much time in the air. And at very steep angles, you're spending a lot of time in the air, but your horizontal velocity isn't very far. I may have said that wrong. At low angles, your horizontal velocity is very fast, but you're spending very little time in the air. At steep angles, you're spending a lot of time in the air, but your horizontal velocity is very slow, so you're not going very far. So it should just be a ranking from the lowest degrees to the highest degrees. And it is 15 degrees, 30 degrees, 45 degrees, 60 degrees, and 75 degrees. And problem solving strategy, conceptualize the problem, categorize it as you can use the maximum height and the range, analyze it using the equations of motion given here, and finalize it. And if you work these problems often enough, and if you really understand the physics behind it, they shouldn't be a problem. Okay, that's it for this. We'll go on with particle in uniform circular motion on the next lecture.